Hi, I'm Killam. Welcome back to this Succeeding in Circuit Theory video series. In this third instalment, we'll be talking about Kirchoffs current and voltage laws and solving problems using them. Let's start with Kirchoffs current law, which basically states that the total sum of currents flowing into a node must be zero. In other words, what flows in must flow out. The two equations on the screen both describe Kirchoffs current law. The small problems, the second equation, what goes in must come out, is fine, but as things get more complex, I prefer to use the top equation. And I always consider currents flowing out to be positive and currents flowing in to be negative. Here are a couple of simple problems for you to try. Pause the video now and calculate the values of I2 and I4 in them. Don't forget to get your polarities correct. So to start off, I'm going to solve Kirchoffs current law for this problem in two different ways. First up, I'm going to say in equals out. So everything on the left-hand side of our equal sign will make an in. Everything on the right side will be an out. On the left, we have 1 amp going in, and we've got those two going out. So we have 1 equals 2 plus I2. That means I2 equals 1 minus 2, which equals -1 amp. Now, hopefully when you solve this problem, you actually ended up with -1 amp. Remember that having the wrong polarity on a number isn't almost right. It's just wrong, unfortunately. So it's very important. We've got to get that right. Now we'll do it the other way. The way that I usually prefer to do it is we go 0 equals the sum of currents flowing out. So we have -1 because it's flowing in. We have plus I2. And we have plus 2. And if we do that, we do the algebra, I2 is going to equal 1 minus 2, which equals -1 amp. So you can see there's no real difference in the difficulty in using either method. But the most important thing is to actually be very, very methodical with these. I'm just going to use 0 equals the sum of the currents. Now, and we'll solve for I4 first, because we know all the currents on this top node except for I4. So it's the easiest one to do. We just go 0 equals, and again, remember, out is positive. So we have -6 plus 2 plus I4. So we'll do a bit of algebra, and I4 equals 6 minus 2, which equals +4 amps. Now, to calculate I2, we have to go down to this node. And the positives and minuses will change because our sort of point of view has changed. So if we look at it, we have -I2, and we have -2 amps, and we have -4 amps. And if we do our algebra, we'll end up with I2 equals -6 amps. Now, I'm going to show you a little trick. If we didn't need to find I4, we could have made this whole area a kind of supernode. And again, Kirchoffs current law works for any sort of planar surface. So if we drew this circle here, all of the lines going in and out, Kirchoffs law must apply to those as well. And if we look at it, we have 6 amps going in. And so on the other end going in, we must have -6 amps, even without having worked out I4. We can go just straight to that. Sometimes that's quite handy when you've got a very complex circuit under your circle and you don't really need to deal with it. Now here's a circuit that looks much more complicated. It's important not to get flustered when things start looking this way. Look carefully at what you were given and what you can easily calculate. There's nothing wrong with rearranging the circuit without changing its electrical connections or combining resistors if it makes things easier for you. Now pause the video and calculate the value of IT. So here's our problem that's just redrawn on the iPad. Now let's just look very carefully at this before we start doing any work. We're looking for IT and the other currents that we know. We know that that current there is 1 amp. We know that current there is 2 amps. Now, at this point, if you're reasonably observant, and you remember what we did last time, we could actually say that everything flowing into and out of, all the currents flowing into and out of that zone, the red marked zone, must add up to 0. And we know the 3 currents. So if we write Kirchoffs current law, 0 equals, remember I take currents out to be positive. So it's positive 1 amp minus 2 amps minus IT equals 0. And we do our algebra, that's going to equal IT equals negative 1 amp. So you can see that that problem was in fact very, very simple. Say if you didn't see that particular shortcut, just undo all of my working here. Say we didn't do that. What we would do then, another approach, would be to combine those 3 resistors. So 1 on 1 plus 1 on 2 plus 1 on 3. Invert that. That gives us a new resistance. Now that resistance happens to be 546 milliohms. Is 546 times 10 to the minus 3 ohms. You could then redraw the circuit. All right, it's 0.546. We have our 1 amp, 2 amp, and we have IT. And again, taking in and out, 0 equals positive 1 minus IT minus 2. IT equals minus 1 amp. So there's not that much extra work combining resistors, but as I said, it's not necessary. And if it's not necessary and you can see the trick involved, it's not really a trick. If you can see the actual shortcut there, then by all means take it. I certainly would. Now we'll move on to Kirchoffs Voltage Law. This states that the sum of voltages around a closed loop must equal 0. Basically, after going around a loop, you end up where you start. Since the start and end points are the same, the voltage difference between them must be 0. Now let's look at this line that says what goes up must come down. So here's our circuit diagram that was on the slide, and we'll just go around it doing Kirchoffs voltage law. Probably the first step, it's not compulsory, but for explanation it makes it easier. Let's let the base here down the bottom be 0 volts. Okay? So if we go through this power supply on the left-hand side, we now know that this voltage up here is actually 10 volts. And we can think of this as climbing 10 stairs. Okay, so we're now 10 stairs up. Now, if we look at this resistor at the top, the left hand is plus and the right hand is minus. So the right hand is more negative than the left. Now, in fact, we're going down 3 steps. So this is now 7 volts. And that's 7 volts with respect to the 0 volts that we've put down the bottom. And finally, we look at the resistor on the right-hand side, and it again, the sign that's closest to where we are is positive, so it's going from plus to minus, so it means it's dropping down. So we have 7 volts minus 7 volts gives us 0 volts. And we're going down 7 stairs. And we're back on the ground floor again. That's basically Kirchoffs voltage law in a nutshell. We can take any loop around a circuit, any closed loop, and it will be true for it. Okay, it doesn't matter. There's no special conditions for it, really. By the way, in this case, I took my loop as being around in this direction, clockwise. I would suggest that you pick a direction and always stick to it. I always use clockwise. I never use anti-clockwise. Now that we've got the explanation out of the way, I'd like to show how I'd actually solve Kirchoffs voltage law around this circuit. So firstly, I wouldn't actually have to pick a 0 volt point, but what I do need to do is have a loop and have it with a direction. So I draw a loop with an arrow on it. Now, I start my equation, 0 equals. And when this loop enters a voltage supply or a component, whichever sign the arrow hits first, that is going to be the sign of the voltage. So this is in fact opposite of the way the basic explanation was. Minus 10 plus 3 plus 7. Now, you might find that your textbook uses the opposite convention, the one that I used in the basic explanation, and that's fine. I would suggest that you stick with whatever your textbook and your lecturer uses. The textbook that I currently use uses the passive convention, which means that if the arrow goes into a minus sign, then you have a minus. If it goes into the plus sign, you have a plus. And now it's time to work through some simple examples. So you should now pause the video and on these 3 circuits on the screen, calculate the value of V1. And again, don't forget to get the polarity correct. In some of these problems, you'll have to use Ohm's law as well. So starting with our first problem, I'll draw our loop in a clockwise direction. And we can pretty much write our Kirchoffs voltage law directly with this, because if we look at each of the voltages, we know all of them except for the value of V1. We just go 0 equals. Now, the arrow goes into the minus sign first, that's negative 10 volts. The arrow goes into the minus sign first, so it's minus V1, plus sign first, so it's plus 6. So doing a little bit of algebra, we have V1, sorry, it's V1, not V. V1 equals negative 4 volts. We'll now go on to the second problem. Now, if we look at this problem now, again, I draw my loop in a clockwise direction. Now, in this case, we don't have all the voltages at the moment, except for V1. We're actually missing 2 voltages. We've got V1 as an unknown, and also the voltage across the 10 kilo ohm resistor is an unknown. So we need to calculate the voltage across that 10 kilo ohm resistor. So in order to do that, we need to determine the current flowing into the 10 kilo ohm resistor. And in this case, we cannot draw a loop, a continuous loop, so that means our current must be 0 amps. So that means that the voltage across this resistor, using Ohm's law, is 0 volts. Now we can write our Kirchoffs voltage law. That's 0 equals minus 10 plus 0 plus V1. And if we do some algebra, we end up with V1 equals 10 volts, positive 10 volts. Now our last example has a current source in it. So on that current source, we don't know the voltage across it unless we work out the rest of the circuit. So again, I'll draw my arrow. And you notice my arrow is in fact going to be going against the actual direction of current in this circuit. That's fine. This arrow is merely a direction that we're doing our calculations on. So if we look at this, we've got two unknowns, the voltage across the current supply and the voltage across the resistor. So we first need to determine the voltage across the resistor. Now, our actual current is going that way. So we have 2 milliamps flowing in this direction through that resistor. So that means this is going to be the positive end of the resistor. This is going to be the negative end of the resistor. And the voltage across the resistor, I'm just going to write voltage 10K equals. It's going to equal 2 times 10 to the minus 3 times 10 times 10 to the 3, which is going to be 20 volts. With the plus being on the right-hand side. So now we'll work out our Kirchoffs voltage law. We have 0 equals minus 10 minus 20 plus V1. And that equals V1 equals 30 volts. Positive 30 volts. Now, this particular problem actually shows you one thing that you're probably not that used to, which is we have a voltage supply, but we have the current flowing into the voltage supply, into the positive of it. The current for a voltage supply can go either in or out, depending upon what the rest of the circuit's doing. So that's it for our simple examples. We'll next go on to a more complex problem using Kirchoffs voltage law. So here's a circuit from earlier in the video that we used to calculate the value of IT using Kirchoffs current law. Now you can pause the video and use Kirchoffs voltage law to calculate the value of VT. Now with this circuit, you are going to actually have to simplify the resistors as well as use Ohm's law and use Kirchoffs voltage law to come up with the answer. So give it a go and then I'll run through it in a minute. So let's start by simplifying the circuit as much as possible. Okay, you can see that these three resistors are in parallel. They're connected at both ends, all three of them. And these three are in parallel as well. So we just go with the top ones. You have 1 on 1, plus 1 on 2, plus 1 on 3, all inverted. And that equals 0.545 ohms. This one, we have 1 on 6, plus 1 on 7, plus 1 on 8, inverted, and that gives us 2.30 ohms. Now I'll redraw the circuit, adding in that simplification. So I'll draw the resistor up here rather than vertical. We have 0.545 ohms. We have 1 amp, 4 ohms. Amps, and 2.3 ohms. Oh, I forgot the plus minus on the VT. So let's look at what we can actually calculate in this circuit. So using Kirchoffs current law, we know that the current here, we remember it from before, it was 1 amp going in that direction. The way we calculated that was 0 equals, and remember we take all the outs to be positive, 1 plus this one minus 2. The question mark equals 1 amp, positive 1 amp. So we've got one amp going out of it. So that means we also have 1 amp flowing in that direction. And now we know the currents and we know resistances, we can use Ohm's law to calculate voltages. For this resistor here, we have 1 amp flowing into this end, so it's 4 volts. This resistor, we have 2.3 volts. This resistor, we have 0.545 volts. So each one of those is just the current multiplied by the resistance, with the plus end of the resistor being where the arrow goes into. And at this point, we have enough voltages around the circuit to be able to write Kirchoffs voltage law and calculate VT. Again, we go clockwise direction, 0 equals, and it's minus VT, minus 0.545 plus 4 minus 2.3. And if we do some algebra, our answer is 1.16 volts. And it's a positive number. And that's it. That problem, when you first looked at it, probably looks a bit nasty, but in fact is relatively straightforward to calculate. So now what we'll do is we'll go on to our final example, which will be the bridge circuit from the second video of this series, which was the resistance video. Here is our bridge circuit from the previous 2 videos. In the resistance video, we calculated the current flowing down the 3 kilo ohm resistor. We'll now go to a diagram of the circuit as to how we left it. So here's the original circuit up top, and then our converted circuit that we use the delta to star transformation on the bottom with the values that we finally calculated in the previous sort of problem. So there's not enough yet on the top diagram to be able to actually calculate the current that we want, which is I1, which is there. Now we can't draw I1 on the bottom diagram because we don't have the 5 kilo ohm resistor. So we're just going to need to calculate more things on the bottom diagram and able to get enough information to calculate it on the top. So let's start by calculating the current through the 4 kilo ohm resistor. I'm just going to write I 4K, and it's going to equal 8.96 divided by a combination of these 2 resistors. Now these 2 resistors are in series, so that's just, we just add them up. It's 5,250 ohms. And that gives us 1.71 milliamps. We can now write that current on our top diagram because 4K exists on the top diagram of 1.71 milliamps. So at this point on the top circuit, we still don't have enough information to be able to calculate I. If you look at it, we can't use Kirchoffs current law because we don't know the current that's in the upper branches of the circuit. So let's just try calculating stuff out. It's often easier in a way just to work out what can I actually calculate, and the answer just tends to fall out rather than trying to have an absolute plan from the beginning. So if I look at the top diagram, we've got two currents and we've got two resistors. So why don't we calculate the voltages across those resistors? So if we look at the voltage for the 3K ohm resistor, it's just going to equal 3K times 2.47 times 10 to the minus 3. And that equals 7.41 volts. Likewise, we can do the same thing on the 4 kilo ohm resistor. 1.71 milliamps times 4K. And that gives us 6.84 volts. And if we look at this circuit now, we can actually draw a loop around the bottom three resistors and calculate Kirchoffs voltage law. So we can do it like that. Getting a bit busy, I know. So let's just write it. And I'm going to write plus minus V5. We have 0 equals negative 6.84 plus V5 plus 7.41. If we do our algebra, we end up with V5 equals negative 570 millivolts. So our value of I1, we can now calculate just using Ohm's law. Our current is our voltage divided by the 5,000 ohm resistor. So we have negative 570 times 10 to the minus 3 divided by 5 times 10 to the 3. And that gives us minus 114 microamps. And that's it. That's our final answer. You can see that this particular problem was quite involved, but as long as we take things step by step by step, it's quite doable. All of these problems are quite doable. It's just that it might take a lot of steps, which makes it extremely important that you're very careful with your units and your signs, because if you get one of those wrong in any of those steps, especially early on, everything will just collapse. And that's pretty much it. We'll wrap it up there. We'll just go to the final slide now. So that's the end of the video. I hope you got something from it. With a combination of Ohm's law, Kirchoffs voltage law, and Kirchoffs current law, you can analyze most DC circuits. There are a few techniques of using them that can improve your efficiency, and we'll go through those later on. In the next video in the series, we'll take a look at equivalent circuits. Hello, out.